Hi everybody, my name is Mariam Khairuddin, and in this presentation I'll be talking about the cooling system and the Raspberry Pi controller with the graphical user interface that we developed for our machine 300 watt LED based light source for endoscopy. As contents of our presentation, we'll be talking about the cooling system parts, the fan connections, the thermostat used, the thermostat control fan. Then we will give the MATLAB Simulink models, the Simulink scope readings, and after that we will start talking about our Raspberry Pi controller, the LED connection. Then we will start with our Raspberry Pi and the steps that are used to start with it. Then we will define the graphical user interface and Kintel. After that, we will give our patient endoscopic graphical user interface that was developed by us. Then the LED Python code results, and after that, we will give some future enhancements. First, let's talk about our cooling system. Our cooling system consists of a 12-volt fan NFB9 Redux with 1600 RPM, manufactured by Noctua in Australia. This fan is considered to be the best choice for a silent fan machine providing a sound with only 17.6 decibel. This fan needs 12 volt and 1.32 watt. The fan is silent because of the presence of a magnet under the rotors, and thus the magnetic field is applied equally on both directions of the fan, providing a more self-stabilization of the rotors and thus having a silent fan. This is also the SSO bearing. Also, the heatsink manufactured by Cooler Master Company is an active cooling system that lays directly behind the LED, adding a thermal grease between them to increase the thermal conduction in the LED cooling system. We must understand that the energy heat transfer is done by conduction and convection. That's why by using 3 heat pipes made from copper and a heat sink from aluminum will absorb heat away from LED, protecting it from high temperature. The heat pipes contain specific fluid that helps in the heat transmission. So, on the LED side, the heat is transferred to the heat pipes and the fluid inside it will start evaporating towards the aluminum side, where all the heat is transferred and the water gets back to its liquid state and returns to the LED side for collecting more heat. The Raspberry Pi can maximum provide a driving voltage of 5 volt, while this silent fan needs a 12 volt. So we need a DC to DC converter, and thus we needed the boost converter MT3608. This fan must not be connected to the drive board, but only to the Raspberry Pi. The AntiC Thermistor is used for the thermal protection. It is connected to the Raspberry Pi, and upon high temperature, there will be a change in the resistance in the thermostat and thus giving a change in the voltage value. And then this will give information for the Raspberry Pi to turn on the fan. Raspberry Pi has no built-in range analog inputs, so we can't connect the thermostat directly to our Raspberry Pi. For that, we used an analog to digital converter, which is MCP3008. It is a cheap converter that can be connected easily to our Pi with no other components needed. It uses SPI bus control, which is supported by Raspberry Pi's GPIO header. And as I mentioned before, the change in temperature on the thermostat allows a change in R2 voltage. So the fan's speed will be controlled indirectly depending on the temperature system detected, where the increase in voltage will be converted into a digital value and provided as a temperature reading through the Raspberry Pi to control the speed on the fan with respect to the temperature reading. In this slide, we tend to show the connection of the fan and the thermostat to the Raspberry Pi. The diode is used to prevent the fan from damaging the transistor by the potential voltage flyback when turning the fan off. In fact, the Raspberry Pi's GPIO has a maximum current output of 16 milliampere. This means that the transistor must have an HFE. HFE is the current gain or the amplification factor of the transistor. So the HFE must be high enough to conduct the current needed to run the fan. So we selected a transistor that has an HFE of 150 when conducting 2 ampere, and thus switching 600 milliampere load is not a problem anymore. Modeling and computation simulation, particularly MATLAB Simulink, of a 300-watt LED-based light source to find the optimized solution prior to the development of the real physical prototype, by knowing the issues and the difficulties we may face in manufacturing process before implementing it. Thus, the power box OFM100, which is our power supply, will be modeled as SMPS, forward converter. The LM3433 Texas LED drive converter, pulse width modulation controlled, will be modeled as a buck converter. The current voltage regulating control will be modeled as current voltage control units based on PID controller. And finally, the fan thermistor temperature protection will be modeled as thermistor with motor controlled by voltage PWM generator. Here, we can observe our fully assembled 300-watt LED light source for endoscopy model controlled by PWM. On the left side, we have forward converter controlled by voltage regulator, where the user inputs the voltage value and controls its output. This forward converter gives power to the buck converter. In the middle, we may observe the buck converter, which has two data inputs from the user, the voltage and the current inputs, shown in the diagram. And for our system, the voltage input must be 3.6 volt, which is the value needed for our LED, while the current value is set depending on the need of illumination. On the right side, we may observe the cooling system, which consists of the AntiC or the thermostat and the fan. This is our MATLAB Simulink model for the thermistor controlled fan, or for our cooling system part. So, as temperature increases, the resistance decreases, and thus its voltage increases, controlling the PWM voltage control generator. The PWM generator uses to change the duty cycle output as its input changes, and thus driving an H-bridge DC motor model with a speed related to the input value. The H-bridge is built of 4 switches or transistors that control the flow of current to a load, and in this way we may have a complete control over the DC motor. When a positive current flows from the electrical positive to negative ports, and a positive torque turning effect acts from the mechanical C to R ports, and by using PWM technique to control H-bridge, we can adjust the average value of the voltage driving the motor of the fan, where the average value depends on the duty cycle. Thus, as the temperature increases, the duty cycle increases and the fan motor torque increase. Therefore, the heat-generating device producing 2 watts at time 0 and then at 40 seconds, this increases to 20 watts. The thermistor heats up and its resistance decreases, thereby increasing the voltage across the PWM reference pins. This increases the PWM frequency, which in turn increases the average motor current, and the fan speeds up. These are our Simulink scope readings, the thermistor-controlled fan. So, as the temperature increases, the derived motor voltage from PWM generator increases as well, and then the motor speed increases, so the torque increases, so the temperature of the system decreases as a result. Raspberry Pi 4 is chosen by us to be the controller used for our machine. It enables the user to have a complete desktop experience where he may edit documents, browse the web with a bunch of tabs, open, juggle spreadsheets, or draft a presentation. The user will find the experience smooth and very recognizable, but on a smaller, more efficient, and much more cost-effective machine. Raspberry Pi 4 has many advantages. It is an energy-efficient Raspberry Pi that runs silently and uses far less power than other computers. It comes with Gigabit Ethernet along with onboard wireless networking and Bluetooth. It has a silent burring fan which is also compatible to the Noctua fan which will be used in our machine. Its power supply has a noise filter to keep it silent, and it contains 4 GB RAM. So we use Raspberry Pi 4 because we need to make a graphical user interface and display it on the touch screen. Also, it can be connected to an external hardware for future more programming or editing the programs used and thus developing the machine. Using our machine, the user must be able to control and choose the LED brightness value according to the application. And to change the brightness, we must control the pulse width modulation and the duty cycle of the LED. So first we connected LED and our resistor, where the resistor is connected to pin 12, which has PWM mode. And this resistor is also connected in series to the LED, while the shorter head of the LED is connected to pin 6 of the Raspberry Pi, which is the ground pin. Then, using Python, we set the code which asks the user to enter the brightness value between 0 and 100, and then it uses this value to change the duty cycle of the LED, and thus it controls the LED brightness. After the simulation of the code, the LED will turn on and the brightness is maximum. Then the user will be asked to enter the desirable brightness value. Once entered, LED brightness will be changed into the chosen value, so the user may control the light brightness through the GUI features on the touch screen, and we tested our Python code, and the results will be shown in this presentation. Note that the duty cycle refers to the total amount of time a pulse is on over the duration of the cycle. So for example, 50% brightness gives the duty cycle of 50, and thus half the cycle the LED will be on and the other half of the cycle the LED will be off. Now, talking about how we started with our Raspberry Pi. First, since we didn't start with our hardware connections yet, we tend to use the Raspberry Pi Zero in order to do our coding and our GUI developed. We decided to buy the Raspberry Pi Zero and work on it till we get our hardware parts. Therefore, we set up our Raspberry Pi and then we put the micro SD card in the reader and put it in our computer. Then we downloaded Raspbian operating system from Raspberry Pi website, and we used Balena Etcher to make the OS or the operating system image and set it on the SD card to function normally. After that, the reader is removed and the SD card is put inside the SD card port in the Raspberry Pi. Then we connect our Raspberry Pi to the computer using the USB cable. After the Raspberry Pi connection, we open our command prompt and type ping raspberry pi.local, and we get Raspberry Pi IP address. Finally, we use PuTTY to make an SSH connection between our Raspberry Pi and the PC in order to program our Raspberry Pi. So we enter the IP address and click enter. Then the PuTTY asks us to enter the username and the password of the Raspberry Pi. And by default, the username is Pi, while the password is Raspberry. Kintel is a Python de facto standard GUI package, so most users use Kintel for their graphical user interface. In fact, we tend for our machine to develop a friendly GUI in order to make the experience of our light source efficient and easy. The user may enter the data, save it, edit it, open it, view it whenever he wants using some buttons on the graphical user interface. In this slide, you can see the graphical user interface that we developed using Python and Kintel. This GUI is user-friendly, where the user may press the light brightness checkbox to check if the GUI is taking the orders in the right way. And once the checkbox is pressed, checkbox number 1 is displayed. When you remove the mark on the checkbox or you press it again, checkbox number 0 is displayed. The user may also choose the gender of the patient, and he must set the slider to the value of the desired brightness of LED, and then press load so that the LED is on at the desired brightness value. We need to mention here that there is no relation between the gender of the patient and the value of the LED brightness, and thus in our future graphical user interface, we will not have the option of the gender, but we use this in order for the patient's information to be saved. Moreover, Kintel menu bar is shown where the user may open a saved file or may save as another file, and using help submenu, the user will be given steps that he may follow to use in this GUI. This GUI is not our final graphical user interface, it is the first graphical user interface, and it will be developed and will be changed. Here in this slide, we tend to show the results of our LED brightness Python code, where we simulated our code and set 3 different brightness values as an input, and efficiently the brightness of the LED changed. So you can see if the user set a brightness value of 100, the LED brightness is maximum, while if he chooses a brightness value of 5, the LED brightness is approximately the minimum. As a future enhancement, we may change the LED type CBT140 to CFT90WD. It has the same characteristics as CBT140, same dimming method controls, LED drive current source of 0 to 27 ampere with 3.6 volt input, high color rendering index 92, but it provides higher illumination flux of 6430 lumen at 21 ampere. Testing current, knowing that CBT140 provides only about 2780 lumen at that current point. Thus, CFT90WD will be more comfortable for the doctor. Another future enhancement is by adding an external control system like a tablet. This improvement can be done by computer-to-computer connection, whereas connecting a Raspberry Pi control system through Wi-Fi to the Wi-Fi of the tablet. And thus we can control many systems using the same tablet. The third future enhancement is by replacing the old LM3433SQ, which is the LED drive circuit, by designing a new LED drive PMP8016 assembled board containing TPS92641, specific for higher current application of 40 ampere. PMP8016 assembled board is just a reference design. We can take it as a start point design. It can be designed using Altium software for PC-based electronics design. And the features and the characteristics of this LED drive circuit are displayed in this slide. The fourth future enhancement can be in changing the LM3433SQ LED driver by MAX 16818 driver specific for high brightness application. It is very similar to LM3433, which we will be using in this machine, but with 30 ampere maximum current output, 6 volt to 28 volt input voltage range, the pulse width modulated LED current dimming, the resistor adjustable over voltage protection and switching frequency, and as an output, the output voltage will be 18 volt. These are our references that we used for this presentation, and thank you so much.